Right. Good evening, everyone. Welcome to Decarbonizing Cement Industry, advancing toward ultra-low clinker cements. The cement industry is a major global contributor to carbon dioxide emissions, primarily due to clinker production. This webinar addresses the critical challenge of decarbonizing the sector by advancing ultra-low clinker cements. Today, we are very pleased to have Dr. Mohammad Riaz Ahmad, who is a research assistant professor at the Department of Civil and Environmental Engineering from the Polytechnic University. He will be guiding us through the innovative low carbon binder technologies. So without further ado, please welcome Dr. Ahmad.
Uh, Thank you, Christy, for your kind introduction. Good afternoon, everyone. I hope everyone is feeling good. So thank you for joining this webinar. Before we jump to the main topic, I would like to briefly introduce our department, as this webinar is a part of PolyU CE webinar series 2025-2026. So the Department of Civil and Environmental Engineering, or abbreviated as CEE, is consistently ranked among the best in the world and #1 in the Hong Kong across various subjects, including the civil engineering, transportation engineering, and environmental engineering subjects. Also, we are home to a vibrant research community with 26 of our scholars recognized as being among the world's top 2% scientists. Of course, this is a list from the last year, but this year even we have more than 26 research scholars among this prestigious list. Besides that, CE also houses multiple world-class leaders in the science and technology, which carries the highest academic honors affiliated with the different academies such as Chinese Academy of Sciences, Ministry of Foreign Foreign and China, and also UK and Australian academies. And CE has won numerous large-scale grants, including the 4 themed-based research projects, also research impact funds, collaborative research funds, and also green technology funds. I would like to emphasize that these large-scale projects, they covers a wide range of topics which are very crucial to Hong Kong development, such as resilient infrastructures, also quality, air quality, and sustainable construction materials. CE also offers a range of civil and environmental engineering programs, both at undergrad and also postgrad levels. Besides that, it also offers comprehensive and world-class research facilities for the master's and a PhD student. And our graduates, which are now our alumni, we have a lot of those outstanding alumni which have gone on to hold key position in the government's industry and academia. A few of them you can see in the following in this slide. So if you like to know more about CEE, you can follow us our page. We are very active on the social media, and also we maintain YouTube channels. So where you can find the time to time further updates in the future webinars and also the past webinars. So today I will be presenting my work on the critical topic for the cement industry. And the topic is decarbonizing the cement industry and advances towards the ultra-low clinker cement. So let's begin by understanding the scale of the problem and why is the cement industry such a focal point for the decarbonization effort. So first of all, I would like to mention about the concrete, because cement is an integral part of concrete. Concrete is the second most material consumed on the earth, just behind the water, and it's a very fundamental to the modern life. It is like a friends in every weather because we can take a shelter. If you look at Hong Kong itself, it's like a huge concrete jungle. It houses most skyscrapers in the world than any other city. So we know what is the importance of the concrete. However, concrete contains a cement, which is only 10 to 15% of concrete. But the problem is that this cement causes 80 to 95% of the concrete carbon emission. So if we talk about the compound effect of only cement, which is just 10 to 15%, however, for the global emission, it causes 6 to 8% of the global emission of the total global emission, so which is quite a lot. Otherwise, in the other words, we can say that cement only is the third largest country which produces the carbon emission. Here I have a further breakdown and the carbon footprint from the cement and concrete. If we talk at a building level, concrete is a major contributor. And if we further zoom into the just 1 cubic meter of the concrete, we can see that production of the concrete is majorly dominated by the cement. And if we further go to the magnify it to the 1 bag of cement, we can see that most of the carbon emission from the cement, it is coming from the calcination, like a very high temperature, heating the limestone at very high temperature. And that this temperature is normally 1450 degrees centigrade. And overall, if we construct like a one room, you can say that around 30% of carbon emission comes only from cement. Also, the cement production is still growing at the large scale, and mostly it is dominated by China. According to the estimate, more than 50% of the cement is only produced in the China. So without the intervention, it's not very easy to reduce the direct greenhouse gases emission from the cement. So it will continue to be a problem in the future. So if you see this graph, we are around here. We are almost reaching the peak of the carbon emission from the cement. So it depends on us how we take actions. So if we take actions, then this carbon emission can go down. If we don't take action, this carbon emission will be consistent, will keep consistent. So if we want to meet the Paris Agreement climate goals and keep the temperature below 1.5 degree, the threshold, then we need to take some actions. So to address the issues in the cement industry, there has been various roadmaps across the different regions and countries, such as GCCA and MPA is from Mineral Product Association from UK. GCCA is a global cement and concrete association, and also Europe has its own, America and Germany, they have their own roadmaps that how they aim to reduce the carbon emission from the cement. So this roadmap, they contains various strategies such as carbon capture, storage, and utilizations. They also focus on concrete efficiency, like how to modify the design of the concrete building so we can reduce the usage of concrete. Also, the other approaches are the novel chemistries, low carbon cements. Like we try to find the alternative cementitious materials, not the OPC. And another approach is clinker, like we reduce the clinker factors. Normally, if we talk about supplementary cementitious materials, we use around 10 to 20, 30%, except slags. Of course, the slag can be used in the higher percentage. Besides slag, all of the other materials, their percentage is limited to 10, 20, or maximum 30%. So in our in today's webinar, I will be discussing about this roadmap, like how we can use this, how we can reduce the clinker at a higher level. So we call this kind of a cement ultra low clinker cement. So yeah, now we'll discuss about. First of all, I would like to talk about low carbon cement and clinker technologies. So in the last slide, I discussed like two major technologies. One of them is low carbon cement, or the novel cement chemistries. The other one is a low clinker cement, like we can reduce the amount of clinker. So I will briefly discuss the few others technologies which we can use to prepare the alternative cement. Some of them include carbonatable binders, yeelimite cements, baelite-rich cement, and alkali activated materials. These are not, we are not going to, I'm not going to cover these today. These are the different topics, but there's a significant amount of research being conducted also on these alternative cement chemistries. Today I'll be mainly covering on supplementary cementitious materials and LC cube and how we can prepare the ultra low clinker cement using these two technologies. And about my research, I have recently I have developed more interest in this ultra low clinker cement. And this cement, normally I try to aim to reduce the cement content up to 20 to 30% only. The others, I also study geopolymer binders and bio-based materials, which are not again covered in today's webinar. So what are the ultra low clinker cement? Ultra low, normally, if we talk about the low carbon cements, we try to replace the supplementary materials by 10%, 20, or sometimes 30%. In the ultra low clinker cement, we try to replace the cement contents 50 or even more than 50%. So the approach is very simple. Normally what we do is that we use a little bit of waste or byproduct and we add to a lot of clinkers. And this is still, of course, a low carbon binder. But in today webinar, what we are doing, what we are going is that we are going to discuss how we can add a little bit of clinker to a lot of waste or industrial byproduct, or so-called supplementary cementitious materials. So, but when we replace too much clinker, we encounter several problems. This is just not an straightforward. There are several issues. One of them is mechanical and construction side. We see very slow early strength development and also delayed setting time and workability issues. And this is partly because there is a less cement, which generates Portlandite, and this is responsible for the pozzolanic reaction. And on the durability side, we also face some issues such as when we replace the higher volume of the cement with supplementary material, the cement has a very low pH. So this reduced alkalinity, it can lead to the problems such as the decalcification of CSHL because of the natural carbonation, or it can also lead to a more porous structures, and which can also degrade the long-term durability, which is a very important for the concrete. So in this, my research aims to overcome or address this issue at the same time, while also focusing to prepare the ultra low clinker cement through different strategies such as alkaline activators and optimizing water to binder cement ratios and using super plasticizer to reduce this water to binder cement ratio. Also using some additives such as CSH seeds, calcium hydroxide, sulfate adjustment, and robust curing. So these are the few techniques which we can use to prepare the ultra low clinker cements. So first of all, in the first approach, I have used the fly ash. Why we have used fly ash? Fly ash is still very commonly available material, particularly if we are talking about the Asia and Africa. Although if you can see the figure A and figure B, there's a significant shift in shutting down the coal power plants, particularly in the North America, USA, and also in the Europe. But if you see the trend in the Asia and Africa, because these are the still emerging economies, there is still a lot of coal power plants. They're under construction, and significant amount of fly ash is still underutilized. According to the literature, global recycling rate of this fly ash is nearly 50%, and this recycling rate is much lower in these Asia Pacific countries or African countries. Yeah, and also if you look at this market size of this fly ash, it will be significantly increasing in the coming few years. So first of all, I try to use this fly ash to prepare the ultra low clinker cement. So in this case, what I did is we did like it. We utilized the 80 to 92% fly ash and 8 to 20% clinker only. So we developed the binder. To make this work, what we did, we used the sodium hydroxide to boost the reactivity of fly ash, and we maintained the very low water to binder ratio to by adjusting the super plasticizer. So the main aim was to create the denser structure. Since the if we water to binder ratio is extremely important. If we use a high water to binder ratio, it after the evaporation, it can lead to the porous structure. And I adopted the two curing techniques. One is a curing at 20 degree, the other was the curing at the 40 degree. So what we did observe is that this is the some very technical results. If you see, this was done by ICP. So actually what we did is we pre-dissolved the fly ash into the sodium hydroxide before mixing with the cement. So if you can see that there is a huge boost or increase in this silica, releasing the silica or alumina. So normally at the normal temperatures, if we don't use the sodium hydroxide, there will be very little amount of alumina or silica to react. But if we use some amount of sodium hydroxide, it can help to release a lot of reactive alumina and silica, which can react with the cement and increase the properties of the cement, which is very crucial to the ultra low clinker cement. Besides that, it can also increase the early strength. So you can see here, the results are quite promising according to our testing. And the NaOH, the sodium hydroxide, this technique, it significantly increased the early strength from 1.7 megapascal to around 6 megapascal at the 1 day, which is more than 3 times. And so it's a significant improvement in the compressive strength, and by the 3 days, it can reach around 11 megapascal. And at the 28 days, we still saw that the compressive strength was still higher, and it was around 35 megapascal. However, the significant increase, what we observe is at the 40 degrees centigrade. So temperature, like I mentioned before, curing is extremely important if we want to improve the properties of this ultra low clinker cement, because it can boost the further reaction. And you can see that when we use this 80% fly ash, the compressive strength can reach 60 megapascal, which is a very high strength. Is almost qualified for the structural grade concrete. So these results prove that we can achieve both low carbon and high performance concrete, even we are using very low amount of clinker. So here we studied the properties of the cement, the hydration properties of the cement. You can see that the green and also the blue, like it has a very high hydration degree. It means the more cement is reacting. Also, if you see here, like more amount of the fly ash is reacting when we use this approach. So also then we also study why it happens and what is the fundamental changes when we use this sodium hydroxide into the system. So we observe that the two things happen. First of all, morphology of the main binding gel are more like we can call it glue in the cement. It changes a lot when we use sodium hydroxide. The other things is also changes the chemical composition, our so-called calcium over silica ratios. So we also again study on the different duration. For example, at the what happened at the 7 day or at very early age, what happened at 28 days, or what happened in the long term. So what we see there, we observe that there are 3 different mechanisms which evolves. First of all is the dissolution when we mix this sodium hydroxide in fly ash. There's a tremendous amount of tremendous reaction going on, and there's a significant release in silica and alumina species. And at the 7 days, we can observe we observed 2 types of gels. One of them is a CASH gel, and the other one is a NaSH gel. But with the time, we saw that there are significant changes, and this NaSH gel is changes to cash gels. We also observed that this when we use the high amount of sodium hydroxide, there's a significant increase in capillary pores. So actually using sodium hydroxide or this alkali treatment is not always beneficial. We have to very carefully optimize that what is the optimum content of this sodium hydroxide. So if you see these blue channels, they are represented by capillary pores, and they are very much wider as compared to these figures on the left side, which shows that capillary pores are much lower here. So this was the first approach. Now I will be discussing the second approach. In the second approach, we studied another promising low carbon cement system, which is known as limestone calcined clay system. This is a tremendous amount of research again is going on this particular binding in a significant part of the world. Particularly, this binder is already being utilized in India, also in Cuba, also in a few countries in Africa because of its lower carbon emission. And also this binder can be significantly scaled. Typically, when we talk about LC cube, so we are talking about LC cube 50, which means that we are replacing up to 50% of the cement with the limestone and calcined clay. So this can cut almost, this cement has almost 40% lower carbon emissions. And so the goal of my research was to further reduce the amount of clinker in this system. So what we did that, the problem is that when we want to further reduce the cement, there's a problem because the reactivity of this calcined clay cannot be fully utilized. There is not enough or sufficient calcium hydroxide. So we try to find some industrial waste which can supply calcium hydroxide. So in this case, you can see that we find the carbide slag, which is a perfect candidate. This carbide slag has 80% calcium hydroxide and 50% calcium carbonate, or we also call it as calcite. So it is a source of likely reactive free line. And here we simply compared the LC cube 50 with the limestone against a new mix, and we call these mixes as LC cube CH because this carbide slag is provide additional additional portlandite or calcium hydroxide. So all other mixtures are called CH. If you see in the figure number A that there's a significant increase in the early age strength when we use this calcium carbide, which is a totally a waste materials, and it can significantly boost the early compressive strength, which is also a major issue in this kind of clinker, in this kind of low clinker cement. So it provides a very promising results to us. Besides that, if the second picture is related to environmental performance index as compared to LCQ 50, this LCQ CH cement, they have a slightly lower environmental performance index. Why it happens, we observed that these calcium carbide, it significantly improve the reaction of calcined clays, and the binding gel volume was significantly increased in this system. So that was a system when we replaced only 50% clinker. And in the next approach, what we tried to do that we again created LC cube mixes only with 40 and 30% clinker content. And we test with these two sources of carbide slag. One is the just a raw carbide slag, which has a lot of calcium hydroxide. The other one, what we try to do, we try to calcine this calcium carbide slag. So try to produce the quick limes or calcium oxide. The major idea was that if we use this calcium oxide, we can, it has a very high heat during the early reaction, and it may boost the early age compressive strength. So again, these are the results. The results were not as we expected, but again, very similar to the LC cube 50, slightly lower, of course, but we were. But if you see at the 28 days, the results are very comparable to the LCQ50, and we could further reduce the clinker content in LCQ50 to LCQ40. And if you look at the environmental performance index, because other research, they use commercial calcium hydroxide. This commercial calcium hydroxide actually has a higher amount of carbon emission. So that even more than Portland cement. So it does not make sense to use this kind of commercial calcium hydroxide. So this carbide slag, which is a waste source of calcium hydroxide, it can significantly improve the environmental performance index. The lower is EPI, the good is the material. And at the same time, it can maintain the same compressive strength as LC-Cube 50. Also, if you see that as compared to LC-Cube 50, it significantly improved the reaction of the system. However, everything is not perfect. If you can see that here at this high replacement level, there's a large amount of calcium coming from this calcium hydroxide. It's reduced it significantly actually retarded the hydration of the clinker or hydration of the cement. You can see that the properties of this 20 or 30% cement we have in the system. So it means that, but it also gives us some clue like what is happening. It means if we are able to further improve the reaction of these calcium silicate, tricalcium silicate and dicalcium silicate, it means we can further increase the performance of this LC-Cube 30 and LC-Cube 40 system. However, there was a significant increase in the aluminate minerals C3 and C4F. Overall, there was a reduction in hydration of the clinker. So in the future, we'll try to find some approaches how we can address this problem, and compressive strength, our durability properties could be even better. And further, we looked into the material's microstructure, and we observed that carbide slag actually does not damage microstructure. It actually has a very similar microstructure as compared to LC-Cube 50 and much superior as compared to the normal cement, which was also, you can see here, these are the results from NMR, and we observed that the calcium binding gel is almost in the similar quantity or even slightly higher quantity than LC-Cube 50. And most of this aluminum was also found in other phases such as attongite and AFM phases. And so another approach, how we can reduce the clinker in the cementitious material. This is the third approach. This is our most radical approach and very ambitious, because we just wanted to know what is the absolute minimum amount of clinker we need to trigger the reaction. So we aimed for a very, very ultra low clinker cement, and in this we use the 70% fly ash, 20% GGBS, and 6 to 10% clinker, which is an extremely low clinker. And here we prepared the two set of mixtures. One is a P series, which only contains CH. The other was a mixture which contains the calcium formate and CH. So first we optimize the volume of the percentage of the calcium hydroxide or CH, and we observed that we can achieve around 48 megapascal by using this 2% CH. And further, we try, because the compressive strength is still very low and it does not meet the industry standard. It is around 6 megapascal only. So we try then in the further optimization, we added some calcium formate. And we could see that at 1 day, we could achieve the compressive strength 15.7 megapascal, which is a significant boost in the compressive strength, given that clinker content is only in the range of 6%. So why it happens and how it happens, we further try to study what are the different mechanisms. So we propose that 3 different mechanisms which happens in this kind of system. The first one is that the calcium formate, it aggressively attacks the hydration, the clinker. So, and then it increased the hydration of the clinker at a very, very early age. The second one is a substantial increase in the volume of the CSH gel, because we also have a slag, 20% slag here. We have a calcium hydroxide. So, and we also have calcium formate. So by improving the hydration of the clinker, this system can also increase the reaction of these supplementary materials such as slag and fly ash, because there's a sufficient amount of calcium hydroxide available. The third and the last phenomenon we observed, that there's a high volume of calcium carbonate. Otherwise, we can say that in situ carbonations, which form very tiny calcite particles, which can fill the pores and densify the microstructures. So these observations we saw with the help of the TGA and also with the XRD. If you can see here at the 28 days, as compared to this control mixture, there's a huge increase in the intensity of the calcite mineral. So to summarize, we utilize different approaches. pH optimization is extremely important. Also, the adequate supply of CH, because in this low clinker cement, when OPC is very little, it needs the CH so that it can further react with the lot of waste which is present in this kind of a system. Also, it's important to add some extra gypsum, which we did, especially particularly in case of LC cube system. Otherwise, cement can have some flash setting properties. Again, also particle packing and size and density is also important. However, we did not cover this. We did not cover this topic in our recent research. We also did not study CASS seeding, but these are the techniques which have been reported in the literature to boost the strength. They have not covered yet to study the ultra low clinker cement. However, not a lot of research is available. Also, we studied the low carbon, low water to binder ratio and robust curing. So these are the different techniques which we can utilize to produce the ultra low clinker cement. So a critical question, however, is that do we have enough supplementary cementitious materials for the global transition? So the good news is that there is a vast and diverse range of potential supplementary materials. If you can see these tables, this table lists the numerous industrial byproducts and solid waste. For example, red mud from aluminum productions, incineration bottom ash from waste to energy plants. In fact, Hong Kong is now producing the incineration power plant, and it is estimated that it will be completed this year. And also for the second incineration power plant, it is also planned. So there will be a significant amount of incineration bottom ash which will be generated in the Hong Kong itself also. Also, there's a huge amount of other supplementary materials such as phosphogypsum, waste concrete, mine tailings, and coal ganji. If you can see that actually the volume of generation of these industrial byproducts, it is much more than what is the requirement of the cement. So it just it needs a lot of research. Of course, there's already a lot of research going on. And so it means that we can utilize these large volume of the supplementary materials available to produce this kind of low clinker cement. However, not every material is equally good, such as fly ash, slag. So there's a significant need to invest the money into the research to study the properties of these supplementary cementitious materials. So to do that, I also did some screening, such as to study the chemical composition of these materials. If you see this ternary diagram, I have shown that what is the chemical composition of these materials. From the literature, I gathered some more than 100 of articles. I try to see what is their reactivity, and then I try to check like what is the compatibility of these supplementary materials with the different low carbon binders. This is a simple, very I think a pocket tool to determine like what supplementary materials can be used for what kind of binders based on the reactivity and chemical compositions. Of course, it is still possible, like some information need to be upgraded because supplementary cementitious materials, they have a, even when they are from the different source, they may still have a different reactivity, they still may have a different kind of chemical composition. So it's still, but however, this is a very preliminary guidelines. And I think using just this simple picture, we can very quickly determine and that this kind of materials is suitable for what kind of binders. This is again a very comprehensive table. I'm not going to explain too much about this table. However, I will introduce some key points. First of all, OPC is a very cheap and very versatile, but it has a high environmental cost. So supplementary blended cement and LC cube, they're commercially ready and being used in the several part of world, and they offer significant saving depending how much is the replacement level. In our study, we do up to 80 to even more than 90%. So it means it can actually reduce not only the in terms of cost, but also the environmental emission or carbon emission. However, of course, there are significant technical barriers. It's not, and especially talking about the ultra low clinker cement, it is not a wide practice around the world at this moment. Alkali activated materials and novel clinkers such as CSA, there are also a significant amount of research is going, and in a few countries they are already being used. In the very recently, UK has approved their standard for the alkali activated materials. Also, it is I think in application in the Australia. But these materials, again, they face greater challenges, not only with the cost, also with the supply chains. Also, these new binders, they have a lack of long-term data and standard, which is very, very important. So therefore, when we're talking about the decarbonization of the cement, it requires a very multi and prolonged approach. And so we have to leverage different technologies in the different contexts and different regions, such as a few different kind of binders. They can be very effective in the different kind of environments, such as the geopolymers or magnesium phosphate cements. They're extremely good against the chemical attacks or against the for the nuclear stabilization, nuclear waste stabilization. So it depends. I think we can prioritize, like this binder is suitable for this kind of binder, and we can effectively reduce the carbon emission from the cement. With that, I think I will conclude that I will conclude today's webinar, and thank you very much for your attention, and I will be happy to take any questions.
Thank you very much, Dr. Ahmad, for the very insightful presentation. So now we'll be taking in questions. So feel free to type into the Q&A box, and I'll perhaps start reading some of the questions. From YC Lam, there are two questions. The first one would be comparing sodium hydroxide, fly ash, and GGBS. Which one comes with required early and ultimate strength in lowest cost and highest quality control? In terms of source and quality of additives may affect. Thank you.
Sorry, can you mention the slide?
Mr. White.
Can you repeat the question again, otherwise?
Okay. Comparing sodium hydroxide, fly ash, and GGBS. Which one comes with required early and ultimate strength in lowest cost and highest quality control?
Yeah, okay. So first of all, the GGBS or slag, it provides, of course, early strength. However, GGBS, I assume, is expensive than fly ash. This is a very, and also the reaction rate of fly ash is much slower. So actually there has to be balance. If we want to achieve the high early strength, and but we also want to be very low cost effective, I think we need to use a blend of these materials. So which we actually have done, especially when we are using the calcium formate and calcium hydroxide. So we saw that we can increase the strength up to 15.7 megapascal. But if we are only So I think if we want a very high early strength, GGBS could be a good material, but there could be problem of thermal cracking because of the high heat evaluation. So it will be very beneficial to use some amount of fly ash, but it has to optimize. I think there is no single answer because fly ash does not give early strength, but is cheaper, and GGBS give early strength, but I think is expensive.
Okay, thank you. And then there are three more questions from Mr. YC Lam. The second would be, even though low carbon with less use of cement substitutes is byproduct of electric or steel production, which is high carbon consumed. So in overall, how shall we value the carbon reduction neutrality effectiveness in overall?
Yeah, I think if we are talking about industries, like I mentioned, that they are the significant in the last slide. Uh, one of the most carbon pollution industries are coal power productions. So in this case, if you can see that we have discussed a wide range of supplementary materials, not only fly ash. So of course we cannot. The thing is that we cannot close all the industries, and some industries are not very high polluting environments, such as the coal power production industries. So there are the significant amount of how to say these waste byproducts are available, such as the glass powders, and which has actually quite a good amount of reactivity. And I think it's a very how to say very possible to replace or use these kind of supplementary materials, yeah, from these kind of industries. Yeah.
Thank you. And any byproducts from green energy production can help to apply low carbon concrete?
Any byproduct, I think not necessarily. I mean, it depends again, such as we try to use this carbide slag again, but it depends how much you are using and what is the source of this industry. Again, talking about fly ash, because there's a lot of criticism going on. We need to shut down these coal power plants. Although this fly ash increase the like I actually am trying to address again the earlier question, because it comes from the already carbon intensive industry, so it does not make sense. So I think, but the other industries such as the carbide slag is this product, this calcium, it provides us calcium hydroxide. But if we want to look at the commercial calcium hydroxide, it is extremely carbon intensive. It produces for 1 kg, it produces 1 kg carbon dioxide emission. But this carbide slag, again, is very useful. So I think it can vary from byproduct to byproduct. But in general, I think we can say that in most of the cases, that will be the case, that it will reduce the carbon emission. Yeah, it will lead to a green product. Given that performance is not sacrificed, because this is very important when we are talking about green product. We don't want to sacrifice the performance. So this was also the main aim of our research. We want to reduce the clinker content, but actually this clinker provide a lot of strength. So, but we want to also keep strength. Otherwise, there will be the delay in the construction process. So, we need to find the optimization approach. We did the EPI. That's why we also studied the EPI, Environmental Performance Index, which is correlated with the compressive strength. Yeah.
Right, thank you. And there's a final question from Naitai. But the question is, what's the normal setting time of this kind of mix? And what is the 1 day concrete strength of this mix? Um,
Okay, we did not study at this moment. We have not studied this at the concrete level, but the setting time is very similar to the OPC. Yeah.
all right, that would be the final question. If there are no further questions, for your time, Dr. Hamid. And if anyone else has any questions, would it be possible to reach you through email or?
Yeah, sure. I'm very happy to discuss or answer any questions through the email. Yeah.
Okay, and then I believe your email can be found in the registration link. So,
Yeah, yeah.
okay, and thank you very much, everyone. This is the end of today's seminar, and hopefully see you guys in the next series. Thank you.
Thank you.